Let's cover two more topics related to TCP, and these are about what the research community is doing trying to improve TCP for the future need. First is about how one improves TCP such that it can support long, fat pipe. Okay, what I meant by long pipe is a TCP connection that has long round-trip time, and a fat pipe is that it has high throughput. Okay, and this is what we know. Okay, the sending rate or the throughput should equal the window size divided by round-trip time. So this is 0.1 second. And the rate should be 10 gigabits per second. So you see, the congestion window is essentially the two terms multiply, and that is 1 gigabits and approximately 110 megabyte. So at the sender side, receiver side, 100 megabyte is required to buffer the packets that are in flight. And this is just to maintain one connection, right? If you have 10 connections, that's already 1 gigabyte of memory. If you have 100 connections, that's gonna probably take all your memory away. Okay. This is just one issue. Another issue is this. TCP is actually go back and like. What if you run into a packet loss that is triggered by having 3 duplicate acts? What we do there is we set the window size to half of the window size before the loss event is detected. And you know what? The window size, the number of packets there could be, can be as high as this, because if we divide this by 1500 byte, you get these many packets in flight. So in that case, we'll have to retransmit all the unacted packets. Okay, and half of the window size here. Okay, so that's 41 and 666 something packets that we need to send. The bandwidth consumption there, right? The amount of bandwidth we might be wasting there is very significant. So TCP, the current design, isn't really ideal to support long fat pipes. And this is actually assuming that there's no packet loss at all, no bit error at all. What if we have error? One will have to derive the TCP throughput model considering loss before one can see how big a problem it is to try to support long fat pipes. So let's try to do some derivation here and see if we can come up with the average TCP throughput, okay, provided the window size, round-trip time. The assumption is that let's ignore the slow start, okay? Consider just the congestion avoidance operation and assume that there's always data coming in. And the scenario is very simplistic, which is illustrated here. Over time, the changes of the window size is exactly from half of W increase all the way to W, and W is where the loss will always occur, and therefore we drop the window size back down to half W because this is in congestion avoidance. When there's a loss, drop to half W. When there's a loss at W, drop to half W. Okay. And so it's not hard for you to see what is the average window size? The midpoint here, right? So 3/4 of W. And therefore the throughput is what? The average window size divided by the round-trip time, which is this term here. Now, if we plug in, this is the goal throughput, and this is the round-trip delay. Now, what is the window size now? Well, it will be this term multiplying each other and multiplying the reverse of 3/4. Therefore, it's 4/3 now. So this is actually even bigger than the CWND we're calculating there. So with loss, the amount of memory required to store data higher, the amount of unnecessary retransmission also higher. We can go on and on right, try to derive a more general model. So let me not go over the exact derivation, just, tell you, if the loss probability is L, okay, one can actually come up with the TCP throughput being represented this way. Round trip time here, okay, square root of L here, and the maximum segment size here. Okay. Now, if, take the same example here, take the same setting there. Packet size being 1500 bytes, round trip time being 100 milliseconds, and the goal throughput 10 gigabits per second. In order to achieve so, the loss rate needs to be as slow as this. 2 multiply 10 to the power of negative 10. Okay. Now this is a loss rate that's also impossible pretty much on the internet today. So definitely, we need new versions of TCP to support very high fat pipes going a long way. Another major issue is this, fairness. Okay, let's talk about fairness at this level first, the TCP fairness. Okay, so what we're talking about here, the goal is to make sure that the K TCP sessions will share the same amount of bandwidth if it go across the same link of bandwidth R. So the eventual share of the sending rate or the throughput should be R divided by K. Okay, so in this scenario, what you're seeing is the router in the middle, the capacity is R, and we have 2 connections. So connection 1 here should have half of R, and connection 2 here should have the equal amount. So we have 2 competing TCP sessions, and they're competing for a link with capacity R. So what I'm showing here are the relationship of connection 1 and connection 2's throughput. So one extreme is connection 1 gets the whole R, while connection 2 gets nothing. And this is the other extreme. Connection 2 gets R, while connection 1 gets nothing. The fair point is right here in the middle. Each of them gets half of R. So you see here, the dotted block line is to draw the equal bandwidth share, meaning if the bandwidth of connection 1 and 2 falls on this black line, they'll be fair to each other. Now, the blue line here is actually illustrating, this is actually the boundary, the capacity of the link. Okay? If the sum of connection 1 and 2's throughput goes beyond the blue line, that means congestion is beginning to occur, packets will begin to drop. Now let's say we start from here. Connection 1 having this much throughput, while connection 2 have, very small throughput. As time goes by, we're in congestion avoidance state, so we will continue to do additive increase. Therefore, connection 1's throughput will continue to increase, just like connection 2's throughput will continue to increase. And the characteristic, the value of connection 1 and 2's throughput will fall along this line here with the slope of 1. Now, as it goes beyond the blue line here, this is actually beyond the network capacity, we'll begin to see packet drop. And what we'll see next is what? The 2 of them reducing the throughput to half of the value here. Okay, so this is connection 2's. Connection 2's throughput dropped to half of it. Okay, right down here. Connection 1's throughput dropped to half of it, right down here. Okay. So having a loss, decrease the window size by a factor of 2, and that takes us from here down to here. So this is the current throughput of connection 1 and connection 2. Let's move on, right? It will continue to go additive increase as we are in the congestion avoidance state. Crossing the boundary of blue line, drop packet again, and decrease the window size again. Okay, again by factor of 2. So we go down here. So you see, additive increase, multiplicative decrease. Additive increase, you see, the throughput of connection 1 and 2 are actually what? Approaching the equal bandwidth share. So TCP, between the connections, the mechanism warrants that they will be fair to each other. So we see between TCP connections, they will be fair to each other. But what about TCP to UDP? Multimedia applications actually prefer not to use TCP because TCP has this window size mechanism when there's congestion drop it, right? So the rate, sending rate is actually throttled by the congestion control mechanism. So some of the multimedia applications would prefer UDP, and they would send audio video data at high rate, constant rate without really, adapting to congestion. So would that be fair? Of course not. Okay. And not to mention this, what if you have applications who open up multiple parallel TCP connections, okay, versus other applications who opens one TCP connection at a time to send data? Now consider this case. A link of rate R with 9 existing connections already, right? Then each have R over 9 share of the bandwidth. When there's a new app coming in asking for 1 TCP, that app then, right, will share with 9 existing connections and each get 1/10 of the R. But if the new app comes in and then asks for 9 parallel TCP connections, so that will be what? R dividing by 9 plus 9. And each connection is this much because the new app gets 9 of these, so let's multiply this by 9. New app gets half of R. So a new app designing this way versus a new app designing this way, okay, competing with other existing connections, it's actually hard to make it fair. And you know what? Web browsers, okay, these days do this. Okay, they might start parallel connections to fetch one page. Previously, Internet Explorer were very aggressive. Okay, for example, starting 8 parallel connections, 4 parallel connections to try to fetch web objects in a page. But nowadays, the HTTP consortium actually regulates so that they do not overdo